Morning students, now we are ready with our new numerical and this one is written on the board. Let us solve this numerical. This numerical says that an object is placed in front of a concave mirror of radius of curvature 40 cm at a distance of 10 cm. Find the position, nature and the magnification of the image. This one is very easy numerical. Let us write the quantities which are given. That is radius of curvature, that is minus 40 cm. Because this one is concave mirror and the radius of curvature would be in negative. That is u is equal to minus 10 cm. V is to be find out. When we know the value of r, then we can find the value of f. F is equal to what? R by 2. That is minus 40 upon 2. That is minus 20 cm. And when we know the value of f, then we can also find out the value of v by using the formula 1 upon f is equal to 1 upon v plus 1 upon u. Here 1 upon v can be written like 1 upon f minus 1 upon u. We can put the value that is minus 20 and this one is minus 10, that is 1 upon 10. So here 1 upon v would be equal to what? Minus 1 upon 20 plus 1 by 10. So 1 upon v would be equal to what? 1 upon 10 minus 1 upon 20. 1 upon v would be 20 would be LCM 2 minus 1. That is 1 upon v is equal to 1 by 10 or 1 by 20. That is v is equal to what? 20 centimeter. And the value of v is it positive, then the image would be what? Virtual. The image would be what? Virtual. Now moving to the next, we have to find out the value of the magnification. So for that, m is equal to minus v by u. What would be there? Minus 20 upon minus 10. This can be written like 2. The magnification would be equal to 2 and this is written like I by O. So that I by O is equal to 2. The image, the size of the image would be twice of the size of the object. This one is O. Actually, I should write H dash upon H. Then it would be more clear. H dash upon H. Then h dash upon h would be like this. Then h dash would be equal to this. Because that O seems to be 0. That is why I have just changed this. H dash upon h can also be written so that h dash upon h is equal to 2. That is image. The size of the image is twice of the size of the object. The size of the image is twice of the size of the object. So this one is all about this numerical. I hope you have got this numerical. Thank you. See you in the next lecture. Good morning students, and this welcomes you all. Now we are ready with our new numericals and this one is written on the board. This one is about chapter dual nature of radiation. We are just going to study these numericals which are written on the board. How you solve these kind of numericals? Let us see. In the very first numerical it is given, find the maximum frequency and minimum wavelength of X rays produced by 30 kilovolt electrons. If it is given for the 30 kilovolt electrons, then how do you solve this? What is given here? That is V is equal to 30 kilovolt. This is written like 30 into 10 power 3 volt. The value of V is given what? 30 into 10 power 3 volt. Now we are to find out the value of maximum frequency. The very first we are to get what? We are to get the maximum frequency. How will you get the maximum frequency? We have many of the formulas for this. That E is equal to, we know that E is equal to H nu. Do we have any relation between E and H nu? This kind of relation we are having. And the second one relation between E and V, that is E is equal to EV. We have to put the value that EV is equal to what? H nu. Then what we are to find out? We are to find out nu. So nu is equal to EV upon H. The value of E is 1.6 into 10 power minus 19 and the value of V it is given 30 into 10 power 3 and the value of H is written like 6.6 into 10 power minus 34. Let us solve this. We can solve it like minus 34 plus 34. That means 19 and 3. This one is 11. This one is this and this can be like. Let me solve it. Then it is written like 1, 2, it is written like 7.2 4 into 10 power 18 hertz. 7.24 into 10 power 18 hertz. And what about the next one? The next one, it is asking about the minimum wavelength. Minimum wavelength, how will you get the minimum wavelength of this? How will you get the minimum wavelength of this? Then we have got the value of nu. So we do know that C is equal to nu lambda. The lambda can be written like C upon nu. This can be written like 3 into 10 power 8 upon 7.24 into 10 power 18. This can be solved like, if you are just giving this one, then this one can be 10 power minus 11, that is 30 upon 7.24 into 10 power 11 minus 11 actually. This can be written as 4.14 into 10 power minus 11 meter. This one is what? This one is 4.14 into 10 power minus 11 meter. The next numerical, let us see what it is about. It is about, let me set the camera first. It is about the photoelectric cutoff voltage in a certain experiment is 1.5 volt. What is the maximum kinetic energy of the photoelectrons emitted? It is very important, very easy numerical. That is V naught is given like 1.5 volt. It is asking about K max. And K max is equal to EV naught. We know the formula, that is K max is equal to EV naught. We have put the value, that is 1.6 into 10 power minus 19 into 1.5. We can calculate easily. What would be the calculation of this? The calculation of this would be what? We have to multiply this only. Then this is 2.4 into 10 to the power. What will be the power here? Remember, what will be the power? That is 10 power minus 19 joule. I hope you have got this in these kind of numericals, as this will see you again next lecture. Thank you. Good morning students, as this welcomes you all. Now we are ready with our new topic. This one is numerical topic. Actually this chapter is having less number of numericals, but the numericals which are asked in examination, that I have to solve, and I will tell you how will you solve these numericals. The very first numerical, it is written on board, that is write the nuclear equation for the alpha decay for 86 radon 226, the beta negative decay of 15 phosphorus 32, and the beta positive decay for 6C11. Let me tell you before solving this that when a radioactive element release one of the alpha particles, then the atomic number is decreased by 2 and atomic mass is decreased by 4. What I am saying, when alpha particle is taken out from a radioactive element, then the atomic number is decreased by 2 and atomic mass is decreased by 4. And when a beta negative particle is taken out from a radioactive element, then atomic number is increased by 1 and atomic mass has no effect. Atomic number is increased by 1 and atomic mass has no effect. And when a beta positive decay or beta positive particle is to be taken out, then the atomic number is decreased by 1 and atomic mass remains the same. So here we are just going to solve these equations on the basis of this law. This law was given by Soddy-Fazan-Russell rule. This is also called Soddy-Fazan-Russell rule. It is not in the syllabus, but I will tell you how to solve this. It is 6Ra226. You are told to just take one alpha particle out, then it would become 84 radon 222 plus 2He4. This is also called alpha particle. This is also called alpha particle. That is why I have written here. In another one, if you are writing for 15p32, then what we have to take out? We have to take out one beta positive decay. Here alpha, here beta negative. Then here 16s32 plus electron negative plus energy. And here the C6C11. Here what we are taking? Beta positive decay. It is having a beta positive decay, then 5 boron 11 plus E plus energy. So this is all about this numerical, I hope you have got this numerical. This numerical says that in this numerical what we have to do, we have to remember one of the formula or one of the rule that when alpha particle is taken out from the radioactive element, then the atomic number is decreased by 2 and atomic mass is decreased by 4. And when a beta positive particle is taken out from a radioactive element, then atomic number is decreased by 1 and atomic mass has no effect. And when a beta negative particle is taken out from a radioactive element, then the atomic number is increased by 1 and atomic mass has no effect. So this rule I have applied in this and I got the answer. I hope you have got this numerical. Thank you, as this will see you again next lecture. Good morning students, as this welcomes you all. Now we are ready with our new numerical and that is written on the board. Let us solve this numerical. What this numerical says that a needle of height 1.5 cm is placed at a distance of 20 cm from a concave mirror of focal length 15 cm. At what distance from the mirror should a screen be placed in order to receive a sharp image? And what is the nature and the size of the image? If the needle is moved closer to the mirror, how would the screen have to be moved? Let us solve this. What are the given quantities? The given quantities are the needle of height 1.5 cm. So the size of the object is given, that is 1.5 cm. And it is placed at 20 cm. So this is u is equal to minus 20 cm. And a concave mirror of focal length 15 cm, that is f is equal to minus 15 cm. In the very first, we have to find out the value of what? V. But finding the value of V, we know the mirror formula, that is 1 upon f is equal to 1 upon V plus 1 upon u. Since 1 upon V can be written like 1 upon f minus 1 upon u, we are just going to put the value, that is 1 upon V is equal to minus 1 upon 15 minus plus 1 upon 20. This can be written like what? This can be written like 1 upon 20 minus 1 upon 15. Now here 1 upon V can be written like 15 minus 20 upon 20 into 15. This can be written like what? Minus 5 upon 20 into 15, that is 5 3s are 15, 20 into 3, that is 60, that is minus 1 upon 16, that is V is equal to minus 60 centimeter. The very first value we have got, and this one is V is equal to minus 60 centimeter. And what about the nature and the size of the image? Let us see. We know that M is equal to I by O and this is equal to minus V by U. So we are just going to find out the value of I by 1.5 is equal to minus 60 upon minus 20. This minus cancelled out 3 times it is, that is I is equal to minus 3 into 1.5, that is I is equal to minus 4.5 centimeter. So the size of the image would be what? Minus 4.5 centimeter, and the image is what? Real, inverted and magnified. What I am saying, it would be real, inverted and magnified. Real, inverted and magnified. Now the next one option is asking about if the needle is moved closer to the mirror, how would the screen have to be moved? Let me tell you, when the distance of the needle is less than the focal length of 15 centimeter, the image becomes virtual. So the same cannot be taken on the screen. So there is no requirement of the screen. What I'm saying that if the focal length is less than, if the distance of the needle is less than the focal length of 15 centimeter, the image becomes virtual. The image becomes what? Virtual. So that there is no requirement of the screen. I hope you have got about this numerical, as this will see you again next lecture. Thank you. Students, now we are ready with our new numerical and this numerical is written on the board. Let us start and let us solve this numerical. How will you solve this numerical? This one is very easy numerical. Actually, I will tell you, in this chapter there are numerical, which numerical has been given in this chapter. These are totally based on what? These are totally based on formula. That means apply the formula and get the result. Here we are just going to do the same. What is that? The threshold frequency for a certain matter is 3.3 into 10 power 14 Hertz. If light of frequency 8.2 into 10 power 14 Hertz is incident on the metal, predict the cutoff voltage for the photoelectric emission. For this we know that the Einstein photoelectric equation, that is given like half mv square would be equal to h nu minus nu naught. But half mv square can also be written like ev naught. That is why ev naught can be written like h nu minus nu naught. Here v naught can be written like h nu minus nu naught upon e. What are the quantities which are given? That is nu naught is equal to given 3.3 into 10 power 14 hertz. Nu is given what? 8.2 into 10 power 14 hertz. And we are to find out the value of v naught. H is given what? H is given 6.626 into 10 power minus 34 joule second. And what is the value of E? That is 1.6 into 10 power minus 19 coulomb. We are just putting here. V naught is equal to 6.626 into 10 power minus 34 in bracket 8.2 into 10 power 14 minus 3.3 into 10 power 14 upon this one is 1.6 into 10 power minus 19. We have to solve this equation only and then we can get the answer. This one is a lengthy equation, but we have to solve this equation. Like just subtract 3.3 from 8.2, then we can calculate the value, and the value becomes, when you solve, you'll get the answer. I'm just solving it so fast. That is 6.26 into 10 power minus 34 and 10 power 14. That goes upside, that becomes what? 10 power. This one that becomes 2.0 actually this can become 2.0292 volt. So this would be what? The stopping potential. By using the formula you can calculate, easy calculation it is. When you just subtract 3.3 from 8.2, then you get the answer. And first of all you have to solve what? You have to solve the power, 10 to the power. If you are just solving the 10 to the power, you can just easily solve the answer. I hope you have got this numerical. As this, will see you in the next lecture. Thank you. Good morning students, as this welcomes you all. Now we are ready with our new numerical. This one is obtain the ratio of nuclear radii of gold isotope, that is 79 Au 197, and silver isotope 47 Ag 107. How will you solve this? So for this we have a relation that R is directly proportional to what? A to the power 1 by 3, we know that. Then R1 would directly proportional to A1 power 1 by 3. Then R1 can be written like R0 A1 to power 1 by 3. Likewise, R2 is directly proportional to what? A to the power 1 by 3. Then R2 is equal to R0 A to the power 1 by 3. If you get the ratio of this, then R1 upon R2 is equal to R0 A to the power 1 by 3 upon R0 A to the power 1 by 3. R0 cancelled. That is R1 upon R2 is equal to A1 upon A to power 1 by 3. Likewise, if you are taking is as the first one and this one is at second one, then we can put the value, that is 197 upon 107 power 1 by 3. This one R1 upon R2. So this one is the ratio of what? Radii, nuclear radii of gold isotope and silver isotope. I hope you have got this. This is from the size of the nucleus. This relation is taken from the size of the nucleus. Then we have got the relation, that is 197 upon 107 to the power 1 by 3. This is the ratio of this. Thank you, as this will see you in the next lecture. Good morning students, as this welcomes you all. Now we are ready with our new numerical, and this numerical is about a point object is placed in air. A point object is placed in air at a distance of 40 centimeter. At a distance of what? 40 centimeter from a concave refracting surface of material of refractive index 1.5. Find the position of the image if the radius of curvature of a spherical surface is 10 centimeter. What is that? A point object is placed in air at a distance of 40 centimeter from a concave refracting surface of material of refractive index 1.5, find the position of the image if the radius of curvature of a spherical surface is 10 centimeter. This one is very easy numerical. I can understand. You have got the answer even. How will you solve the given quantities? Let us write the given quantities. That is u is equal to minus 40 centimeter. N2 is equal to given 1.5 because N1 is given 1. Because the refractive index of air, it is kept in air, that is why N1 is taken like 1. The refractive index of air is written like 1. And what about the R? R is given minus 10 centimeter. Because this one is concave refracting surface. We have to find out the value of V. By which formula we can calculate the value of V? Do we know? Thus, we know that N2 upon V minus N1 upon U is equal to N2 minus N1 by R. We have proved this formula. So by applying this formula, we are just going to get 1.5 upon V minus plus, that is 1 upon 40, that is 1.5 minus 1 upon minus 10. How will you solve this? 1.5 upon V plus 1 by 40 would be equal to 0.5 upon what? 10. So this particular quantity can be taken. That side, this one is 1.5 upon V would be equal to minus 0.5 by 10 minus 1 upon 40. We can solve it out. How? We are going to take 40 as LCM, then 40 here, 0.5 into 4, that would be 2, then it would be minus 2 and minus 1. This can be written like what? 1.5 upon V is equal to minus 3 by 40. Then it can also be written like what? It can be written like 1 upon V is equal to minus 3 upon 1.5 into 40. This can be written like what? 2 times. And this can be written like 20. So 1 upon V is equal to minus 1 by 20. Then V is equal to minus 20 centimeter. So the image is formed at 20 centimeter, and this one is given in negative, that is minus 20 centimeter. So the image will be formed at the same size. The image will be formed at the same size. As U and V both are in negative, that means image is formed at the same size. So this one is all about this derivation. I hope you have got this derivation. Thank you. Good morning, students. As this welcomes you all, now we are ready with our new numerical, and this one is what is the momentum and de Broglie wavelength of the electron with kinetic energy 120 electron volt. When the kinetic energy is given in electron volt, we can convert it into joule. Like that, K is equal to 120 eV. This can be written like 120 into 1.6 into 10 power minus 19 joule. This can be written like this. So now we are to find out the momentum. The momentum can be written like, as we know that K is equal to half mv square. Then this can be written like 2K is equal to mv square. This can be written like 2mk is equal to mv whole square. This can be written like P square is equal to 2mk. This can be P is equal to under 2mk. We can put the value, that is 2 into 9.1 into 10 power minus 31 as the mass of the electron we are just putting. And the kinetic energy which is given 1.6 into 10 power minus 19 into 120. Let us solve this particular, then we can get the answer. As I have solved, this would come 5.91 into 10 power minus 24 kilogram meter per second. Now, the next one it is asking about de Broglie wavelength, then lambda becomes h upon p. What is that? 6.626 into 10 power minus 34 upon 5.91 into 10 power minus 24. When we cut this becomes 10 power minus 10, and that becomes 5.91, that is 1 point, this one is 1, this one is again 1, 6 meter. This can also be written like 1.116 angstrom, as we know that 1 angstrom is equal to 10 power minus 10 meter. That is why it is written like this. I hope you have got this numerical, as this will see you in the next lecture. Thank you. Students, as this welcomes you all, now we are ready with our new numerical, the chapter optics. And this one is very important numerical for your syllabus. This comes in examination. Actually, this has come in examination in CBSE 2019. So remember this, how to solve this type of numerical. Okay, let us solve this numerical. The very first, the question is asking about find the distance of the final image from the third lens. Focal length of lens first is 0.1 meter, lens second is minus 0.1 meter, and lens third is 0.3 meter. So what is given here, that f1 is equal to 0.1 meter. This can be written like 10 centimeter. f2 can be what? Minus 0.1 meter, that can be written like minus 10 centimeter. f3 can be what? 0.3 meter, that is equal to 30 centimeter. What is given here? We are going to solve it for first lens. So for lens first, if you are going to solve the image formation for the first lens, then we can write u1 is equal to minus 0.3 meter, which is equal to 30 centimeter. And we know that the value of f1 is given like 10 centimeter. This value would be negative because it is due to the sign cartesian. Then what would be the value of v1? We can apply the formula 1 upon f1 is equal to 1 upon v1 minus 1 upon u1. From here we can find out that 1 upon v1 is equal to 1 upon f1 plus 1 upon u1. We are just going to put the value here. And what we get, that is 1 upon v1 is equal to 1 upon 10 minus 1 upon 30. This can be what? 30 is LCM, then 3 minus 1. That is 1 by v1. v1 is equal to 30 by 2. 30 by 2, that is 15 centimeter. 15 centimeter. Just because of the calculation, I have converted these quantities, these meter quantities into centimeter. That is why I am writing v1 is equal to 15 centimeter here. We have got the value of v1. That means the image of the first lens would be at 15 centimeter. Now we are to get for the second lens. Where would be the image of the second lens? So for the image of the second lens, remember one thing, we have to minus, subtract for the value of u2 for lens second. For u2 value, we have to subtract this particular distance from the v1 value. That is 15 minus 0.005 meter, that means 5 centimeter. This can be written like what? 10 centimeter. It is the value of u2. It is the value of u2. And remember one thing, it cannot be taken in negative term. And what is the value of f2? f2 can be minus 10 centimeter. Then what would be the value of v2? v2 can be written like 1 upon f2 plus 1 upon u2 by this formula, by this relation. I am writing it directly. That is 1 upon minus 10 plus 1 upon 10. That becomes 1 upon v2 is equal to 0. That means v2 is equal to 1 upon 0. That becomes infinite. The value of v2 becomes infinite. Then we can find out the value of what? We can find the value of v3. For the value of v3, we have to do it as the same order for lens number 3. For the lens number 3, we are just going to put the values. And this particular distance works as a u3. So for lens third, we are just going to solve this. 1 upon v3 would be equal to 1 upon f3 plus 1 upon u3. That would be 1 upon 10, not 1 upon 10, this would be 30 centimeter. And what is the value of u3? As I said, that infinite would be the value of u3. The value what we are getting from here, that would be the value of u3 because it is infinite. And infinite minus, if we are infinite minus 0.1 meter, that is 10 centimeter, then that is also infinite. That is why 1 upon v3 would be equal to 1 by 30. That is v3 is equal to 30 centimeter. So this would be the final image. So the final image would be at 30 centimeter from the third lens. What is that? the final image would be at 30 centimeter from the third lens. I hope you have got this derivation. This one was very easy derivation. One by one we have to solve and we have to find out the value of the distances of the images from the lens. The very first we have got V1 and the separation between two lenses given, that is 5 centimeter. That is, we have subtracted the 5 centimeter and we have put the value, and we got the value of V2, that is infinite, and we have got the value of V3. I hope you have got this derivation. As this, will see you again in the next lecture. Students, now we are ready with our new numerical, and this one is show that the wavelength of electromagnetic radiation is equal to the de Broglie wavelength of its quantum. So let us solve this derivation. This is a kind of derivation. This is not a numerical. This is a kind of derivation. So we are just going to solve this. We know that the momentum of a photon is given by what? P is equal to h by lambda. This implies that lambda is equal to h by p. This one is the question number 1. And the de Broglie wavelength is given by, how will you give? That is, lambda is equal to h upon mv, and that can also be written like h upon p. By this equation 1 and 2, we can say that the wavelength of electromagnetic radiation is equal to the de Broglie wavelength of its quantum. This was very easy. And then we have got what? The momentum of a photon is given by, we know that is P is equal to h upon lambda, then lambda is equal to h by p. Then we have calculated, we have solved. I hope you have got this easy derivation. Thank you. Students, as this welcomes you all. Now we are ready with our new numericals. That numericals are written on the board. We are just going to solve these two numericals of chapter optics. This one is chapter number 9, ray optics actually. Ray optics. We are going to solve the numerical of this chapter. The very first numerical which is written on the board, that is two lenses, one diverging of power 2 diopters and other converging of power 6 diopters are combined together. Calculate the focal length and power of the combination. This one is very important, a very easy numerical. As we have seen here, I have written that cbse 2009. It has come in cbse 2009. So let us solve this numerical. The power of a diverging lens is always taken in negative, that is -2 diopter. The second one, the given quantity, which is P2 is equal to +6 diopter. The formula for the combination P is equal to P1 plus P2. So -2 plus 6, that is what? +4 diopter. +4 diopter. Okay. So now the next one is find the focal length. So what would be the focal length? F is equal to, we know that 100 upon P for the centimeter. So 100 upon 4, that is 25 centimeter. So the combination, the focal length of the combination is 25 centimeter and the power is +4 diopter. +4 diopter. So this one is all about this first numerical, and this one was very easy numerical as we have seen. The next one numerical is a convex lens of focal length 10 cm and concave lens of focal length 20 cm are kept 5 cm apart. There are two different kind of numericals. One is combination here also, but here that is having some separation, that is 5 cm. So let us see what happens. The focal length of convex lens, we are taking f1 as 10 cm and f2 as -20 cm. X can be given as 5 cm. And the formula which is used here, that is 1 upon f is equal to 1 upon f1 plus 1 upon f2 minus x upon f1. Remember this formula. What is the formula? When the separation are given between two of the lenses, then we use this formula and we have to calculate the value. That is 1 by 10 minus 1 upon 20 minus plus upon 1 upon 10 into, that becomes 20 is LCM in these two, then 2 minus 1 plus 5 by, what is that? 200. This can be written like 1 upon 20 plus 5 by 200, 1 upon. Then 1 upon f can be written like what? 200 divided by LCM as, then here 10 plus 5. This is written like 15 upon 200, that is 1 upon 5. That is f is equal to 200 upon 15. Let us cut this. 5 4s are 20, 5 3s are 15. That is 40 by 3. And this can be 3 1s are 3, 3 3s are 9, 13.33 centimeters. 13.33 centimeters. So this one will be the focal length of the combination. I hope you have got this numerical, these two numericals, and these are the very easy numericals here. We have calculated the value of this. Thank you. I'll just see you in next lecture.